Go into the next topic with respective to the second module, which is pertaining with scaling and small geometry effects and along with MOSFET capacitances. So the purpose of this particular topic is we need to shrink the size of the IC. When you're shrinking the size, you have to have a different dimension. So the dimension exists as it is, but you have to scale it. You have to have a parameter which has to be scaled. Normally we write the scale on the graph. So 1 centimeter is equal to 10 volts or 1 centimeter is equal to 1 meter. But that doesn't represent that it is 1 meter. Then when you go back and scale up, you do the reverse procedure. If you have 5 blocks on your graph, it is nothing but 5 meters, because one block represents 1 meter. So this is how the scaling helps us, and we are all quite familiar by now, I hope. So we'll look into this topic now. Now we discuss a problem which is based on 3 input NAND gate. So sketch a 3 input NAND gate with transistor widths chosen to achieve effective rise and fall resistance. So we need to find out the resistances, and there are some ratios given. So you have to go along with finding out the transition between the fall and the rise. So we have the figure in the next slide. It shows 3 NMOS transistors. How to construct an AND gate is by considering NMOS transistors in series. We have already seen a 2 input NAND gate. So NMOS is in series, PMOS is in parallel. Therefore we get the resistances as well as the capacitances. Along with that we can go along with the diagram. So this is a 3 input NAND gate. 1, 2, 3, 3 input, and the inputs are shorted with respective to the NMOS and PMOS, and the ratios are given here. PMOS is normally given as, in this case example, the ratio or the width is given here as 2, 2, 2, whereas for NMOS it is 3, 3, 3. As a result, what should happen to the respective capacitances and the resistances? Resistances are divided by the width factor given across the device, and the capacitances are multiplied. So when we have the representation, this is how we have the representation with respective to the capacitors alone. So you have three PMOS transistors with the width given as 2, and the 3 capacitances associated are the source, drain and the gate. So the 3 capacitances are shown like 2C, 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 3 such. And similarly here the width is 3. Therefore here also we have 3 capacitances. One is the gate, one is the source, and the other one is the one is the drain and the other one is the source. Like that it is in 3 series. Therefore we have the respective capacitances. And we will simplify this by considering a common, since the gates are commonly connected to the input. So the gate will have 3 plus 2, 5C, and the next diagram shows you. So 3 inputs are common, and therefore 3 plus 2 will give you 5C. So gate capacitances for every device is considered here as 5C, and the ratios remain the same. So now we will now look into the NMOS device. So NMOS device, normally we consider the drain capacitances. So the drain capacitance has been considered, and when you look into this PMOS, you had 2C, 2C, 2C. So the drain capacitance of the PMOS together, the lump of this is 6, and the drain capacitance of this particular drain of this particular capacitance, drain capacitance of this particular transistor is 3C, and this was 2C, this was 2C. So together they combine, this was also 2C. So they combine and form 6C. So this gives you 6C plus the 3C of the drain capacitance here. That is why we have it as 9C. So only this transistor, only the top NMOS transistor will have this capacitance 9C, rest all will remain as 3C. So that was with respective to the normal representation. Now we will find out for the falling, as has been told in the problem. For the falling edge we need to find out. So when you look, this is nothing but falling. Falling is when the input is 1 to 0. It is falling from 1 to 0. So when the input is 1, you will have NMOS transistors going into on state. Therefore, the NMOS transistors are going into on state and the resistances. So now I have to replace the transistor with a resistor and a switch. So here I simply consider the resistor and the ratio was given to be 3. Therefore, it is R by 3, R by 3, R by 3. The capacitances remain to be 3C, 3C. Since this has the bulk of the top PMOS transistors, this capacitance is equal to 9C. So this is the equivalent circuit for the falling output transition. And this is how we have the representation, equivalent circuit. Next, when I take the rising edge is from 0 to 1. So when it is 0, NMOS is off, and when it is 0, PMOS is on. Therefore, we assume the top transistor, PMOS transistor, to be on. But here, since the inputs, 3 inputs are given, there are 8 states. So since the 3 inputs are given, the states are from 0, 0, 0 up to 1, 1, 1. 3 inputs. So here worst case has been considered. So the upper 2 inputs are 1 and the bottom one falls to 0. So in the rising edge situation, the inputs are considered to be 1, 1, 0. So when it is 1, 1, 0, obviously the upper 2 transistors of the PMOS are off and the bottom one only is 1. So when it is 1, 1, 0, this is the input being forced. When it is 1, you have all the inputs of the NMOS on, and you have 2 inputs of PMOS off, and only one PMOS is worth representing here with this input. So when you consider this, you have the resistance of PMOS as 2R. 2R divided by 2 will give you R, and this capacitance is 2C. So that 2C and this capacitors of NMOS combined together is 9C, and you have 3C and you have 3C. This is for the rising edge. And here, since the last input is 0, the last transistor is an open circuit. So this has no representation, and therefore the resistance is not shown here. Only the capacitance has a role to play. Now we'll look into the transient response. So applying RC model to a step response of a first order system. So we have the first order system which has only R and C component. If it is second order, you will have 2 such stages. So this is a simple representation, and the transfer function is given as 1 by 1 plus SRC, and this is the output with respect to a step response. So this is the first order RC system. Now what is the purpose of going for this first order RC system is, we'll find out, since this has a component of R and C. Therefore we are going for this first order system. Now the tau, which is the delay constant, is given as RC. So the propagation delay is the time which V out reaches to VDD by 2, as we have already discussed. Therefore TPD is given as RC ln of n. So this is the ln value, and it has been given as ln 2, but all the while we can't take it as ln 2 because it has its own differences. Therefore it has been found out to be 0.69, which is cumbersome, and therefore we finally restrict ourselves to reduce that parameter ln 2 to be neglected, and therefore the propagation delay is given to us as only RC. So in a first order system, the propagation delay is found out to be only RC, where R is the effective resistance. Therefore finally we conclude telling that delay can be calculated using this representation called as RC. Now we consider the second order system. You have 2 such stages, R1 C1, R2 C2, and you have 2 nodes N1 and V out, which in turn can be referred here as N2. So when we have the transfer function is given by 1 by 1 plus S into R1 C1 plus R1 R2 into C2 plus S square, and all the R components and the C components in series. So there are 2 poles, real poles, and the step response is given by this equation. So this becomes little cumbersome, and therefore the conclusion here derived is, what is the propagation delay in a second order system is this much. So this is very complicated if you look into this. Therefore the equations are complicated, and therefore what is it we require in CMOS? CMOS is meant for simplification. Therefore, we can have it in a better representation. Therefore, it is further approximated as a first order system with a single time constant. There are two time constants, 1 and 2. So many parameters which can be looking as complicated. Therefore, we simply split them and show tau as tau1 plus tau2. So it is the first stage R1 C1 and the second stage R1 C1 R1 plus R2 whole of C. So this is how the second order system will have the propagation delay, which is considered as the sum. So when you have a representation of R and C, tau1 gives tau2, tau3 are represented with these values. So R1 C1 plus R2, when you just represent them, this is how the values are got. And the error from the first order system will be less than 7%, and if there are two time constants, it will be less than 15%. So this is the second order response when you compare it to first order approximation. Blue color is in second order, black color is in first order representation. So this is a simple comparison between the first order and second order response. Next we discuss a topic which is called as Elmore delay. So what is the purpose of Elmore delay? We have just now seen delay and we have seen propagation delay. So what is Elmore delay? In general, most circuits of interest can be represented as RC tree. So we have seen now circuits are having a component of R and C, and therefore RC is always there. So we consider it as a tree. Tree is open, therefore there are no loops. So the root of the tree is the voltage source. So representation, in order to understand what is Elmore delay, we have to take the RC component of the RC circuit as a tree structure which has no loop. Then if it is a tree, there is something called as the root, then you have the branch, then you have the leaf. So the root of the tree is the voltage source and the leaves are the capacitors, because capacitors are always connected in the end either to the supply or to the ground. If it is PMOS, it is connected to the supply. If it is NMOS, it is connected to the ground. So the Elmore delay model estimates the delay from a source switching to one of the leaf nodes, changing as the sum over each node I of the capacitance Ci on the node. Okay, the representation of Elmore delay is simple, given as summation of I and given as a resistance which is found from source to every node, where I is the number of nodes to every node and ICI also is the capacitance at that particular node. So I here is nothing but the node. I is the number of nodes. So compute the Elmore delay for V out in the second order system. So we have a second order system. This is the output and we need to find out the delay at this particular interval from source to the output. When you look into this, there are two nodes N1 and N2. N2 here is nothing but the V out, and you have R1, R2 and C1, C2. So please try. On the same grounds, we will now try to estimate the propagation delay for a unit inverter. So unit inverter has been reduced to the equivalent circuit, and it has been found that it has R as the resistance and the capacitance is 3C, which is considered as the diffusion capacitance of the parasitic capacitance, and across the output it's all called as the load capacitance, and it is given by 3MC. So for this circuit we need to find out the propagation delay. So roughly telling, this can be considered as the source and this is considered as the output. So whatever are the values of R and C coming across in this path is considered. So probably it may be equal to R into 3C plus R into 3MC. Okay, let us now look. So figure shows an equivalent circuit from the earlier diagram, and they have 3 units of gate capacitance and therefore it forms 3MC. So the output has the capacitance is 3C, called as the drain capacitance or the parasitic capacitance, and the parasitic capacitance is given by 3C, driver capacitance is given by 3MC. Therefore the Elmore delay is calculated by 3 plus 3MC RC, or 3RC plus 3RC plus 3MRC, and if this is taken as common, the delay is found out to be 3 plus 3MRC. So based on the same example, if the driver is W times unit size, so the driver transistors are W times wide. So we have the width given as W. So if the width is given as W, then the resistance has to be divided by W, capacitance need to be multiplied by W. Therefore, since this is the load capacitance, W has no impact on the load capacitance, only on the diffusion capacitances or the drain and the source capacitance there is an effect of the width. So the circuit is quite self-explaining, telling what is the values of R and C. So the Elmore delay is calculated plus, okay, first is the simplified version has been given. If you want, you can have it as R. So what is the R given here is R by W with respective to this particular node into 3WC. 3WC, which is equal to 3RC. 3RC. This is at node 1. So this is at node 1. Next, at node 2, this would be equal to RW plus 3MC. So node 2, it would be 3MC into R by W. So the sum of this will give you 3 plus 3M RC component. If it is taken out, it is 3 plus 3M by W. So this is the expression. If you sum up at this plus this, if you sum up, you will get this. So define the fan out of a gate. Therefore, if you just consider the ratio, fan out is given by the ratio of the load capacitance to the input capacitance. So what is the load capacitance? So therefore we call it as fan out as H. H is given as ratio of the load capacitance. What is the load capacitance? It is 3MC. And what is the gate capacitance? Load capacitance is 3MC, ratio of input capacitance. So diffusion capacitance is not considered. Therefore, the load capacitance is 3MC and the input is 3WC. So this turns out to be M by W. So H is equal to M by W. This gets cancelled, this gets cancelled, and the delay can be written as M by W can be replaced as H, which is the representation for fan out. Next, we go out for another example. If a unit transistor has R is equal to 10K, C is equal to 0.1 femtofarad. Femto is 10 power minus 15. In a 65 nanometer process, compute the delay in picoseconds. If compute the delay of the inverter for this particular inverter if the fan out is H. So the output is being driven, the output is driving 4 different inverters. Therefore, the fan out is equal to 4 since it is driving 4 different devices. So we need to find out the propagation delay. So in RC is the time propagation delay. In 65 nanometer process, this has been given as R is equal to 10K, 60 and capacitance is 0.1 femtofarad. Femto is 10 power minus 15, and if you substitute, it turns out to be 1 picosecond. So the delay is 1 picosecond. So if there is a delay of 1 picosecond and it has to drive 4 different devices, what would be the total delay? Therefore, for H is equal to 4, the delay would be equal to 3 plus 3h into 1 picosecond, it would be 15 picoseconds. So almost 4 times. 1 picosecond for each, for one gate, but if it has to drive 4 different gates, it becomes 15 picoseconds. So this is called as the fan out inverter delay, and this is the representation. Next we have another representation. So normally normal delay is called as D, which is given by propagation delay divided by the tau, which is normal delay relative to this inverter delay. So the delay of the fan out of H inverter can be written in normalized delay as, so in other words, D can be represented as H plus 1. D can be represented as H plus 1, assuming that diffusion capacitance approximately equals phi gate capacitance. So if that is the case, what is the value of H? The H value was found out to be 4, and therefore it gives you phi tau. So next we have another example, which is estimate the propagation delay for fall and rise if it is a 3 input NAND gate and it has loaded with H identical NAND gates. So this is the diagram given. Already it has been represented. The capacitance here is 9 plus 5H and it has R by 3, R by 3, R by 3 everywhere. So each NAND gate load represents 5 units of gate capacitance on the given input. So what does this representation show? It is for a falling transition. It is for a falling transition, that is for from 1 to 0. If it is from 1 to 0, PMOS is completely inactive and NMOS is the one which is going to be active. Therefore, all the representations are shown for NMOS devices. Node N1, we have 3 different nodes. We have N1, N2 and the final node, which is the output. So what is happening at node N1? What is the value of R and C at node N1? Node N1 has a capacitance of 3C and a resistance of R by 3. Similarly, node N2 has a capacitance of 3C, and from here to this particular, from the node N2 to the ground, what is the capacitance? It is what is the resistance? It is the sum of two resistances, R by 3 plus R by 3. Alright. Similarly, node 3, the last node is here. So it is this capacitance 9 plus 5H divided into R by 3 plus R by 3 plus R by 3. So these are the capacitances at and the resistances at the respective nodes N1, N2 and N3. Therefore, the delay for this is given by 3C into R by 3 plus 3C into R by 3 plus R by 3 plus 9 plus 5HC into R by 3 plus R by 3 plus R by 3 turns out to be 12 plus 5HRC. So this is for the falling output. Falling output is from, transition is from 1 to 0, and when it is 1 to 0, PMOS is off. Therefore, only NMOS is considered. PMOS is off. Therefore, we have only NMOS transistors, 3 NMOS transistors which are in series. Next, we will look at the representation for the falling transition. So Y is pulled up to VDD. Alright, so when we have this, the worst case is considered, and only one for the input as 110. Therefore, this is completely off, and the two transistors on the top is also off. So on transistor contributes the parasitic capacitance. So you have again node Y. So at node Y, that is at particular node here, you have the capacitances 9 plus 5HC and the resistance from VDD. Okay, since it is falling transition, which is with respective to this, becomes the source now. From here to here, from here to here we need to talk. Therefore, it is 9 plus 5H into R. And node 2 has 3C, and The relevant resistance is only R, not R plus 3, because the output is being charged only through R. Yeah, we shouldn't take this because I told you the reference is only from here to here. So only this resistance comes into picture and all capacitances comes into picture. Therefore, the delay is calculated as R into 9 plus 5H plus R into 3C plus R into 3C. Let us see now. Okay. So that is how the delay is calculated. Turns out to be 15 plus 5H RC. Next, we have another representation. Estimate the contamination delay. So we need to calculate the contamination delay for this circuit, which is having a capacitance of 9 plus 5HC and the resistances as R by 3, R by 3, R by 3, and when it is PMOS coming into picture, you have the capacitance as 9 plus 5HC and the resistances are R. So figure A shows the equivalent circuit and the delay is, so the contamination delay is given by 9 plus 5H capacitance value 5HC into R, because R by 3 plus R by 3 plus R by 3, it is 3 times. Therefore, it turns out to be 3R by 3, which is equal to R. Therefore, the delay is 9 plus 5H RC. Similarly, for the rising edge, the best case is that all 3 PMOS transistors turn on 111. When the inputs are 111, all N devices are 0. Therefore, the N transistors turn off and N1 and N0 are not connected. N1 and N2, the two nodes are not connected and they do not contribute to delay. So the parallel transistors deliver 3 times as much as current as shown in figure 3. Therefore, the contamination delay is given by 3 times of the earlier ones. So it is 3R plus 9 by 5HC and it has been reduced 3 plus 5 by 3 HRC. So this is the contamination delay when you have 3 resistances in parallel.